let's continue with our discussion on differential equations. And like I said last time, we're going to learn how to drive before we open the hood and see how these methods to solve numerically solve ordinary differential equations work, specifically initial value problems. We learned about ODEint last time, and we applied it to the problem of cooking a lobster or a vegetable either boiling it in a fluid or using radiation in the oven. And we used ODEint. All it required was the right-hand side of that differential equation and an initial condition and a sequence of points in time at which we want to approximate the solution of that ODE. So we played with that model a little bit in Python, and we implemented both right-hand sides. They're provided here for you for your convenience as you use them for your homework. And also, the session was recorded, will be posted online, so if you want to review that. Now, similar to when we were using Fsolve, if you remember with the lobster cooking problem, we had to pass information about the heat transfer coefficient H, T infinity, right, for the water or the oil or the air, and T infinity for the oven, and maybe some other parameters, right? So, and every time we had to change those parameters, we wanted to change those parameters, we had to go back into the right-hand side and change the value or put a global variable, which I really dislike, and then go back, change that global variable. A better approach, a more programming-oriented approach is to try to pass everything as an argument, as much as you can as an argument. Similar to Fsolve, ODEint allows you to pass arguments to any right-hand side routine that you develop. So suppose that your right-hand side, so by definition, the right-hand side needs at least 2 arguments for ODEint to work. The first argument is the dependent variable. The second argument is the independent variable. And then you can put as many remaining arguments as you like. Okay, so let's suppose those could be heat transfer coefficient, T infinity, emissivity, et cetera, a bunch of other parameters, the length of the lobster, the diameter, et cetera, the mass of it, and so on. So you could pass however many arguments you want. ODEint allows you to do that. Similarly with Fsolve. So with ODEint, you put the standard right-hand side, name of the right-hand side routine, your initial condition, your sequence of time points, but then you can add an argument called args, and you list the arguments here the same way they are listed in your right-hand side function. So in your right-hand side routine. Internally, ODEint will know, it will always call the right-hand side with the current value of the dependent variable, the current value of time t, and then it will append all of those arguments so that you can call that function without your right-hand side routine without any issues. So it just makes it a little bit more convenient. You might choose to do that, to use this feature or not. It's up to you. All right. So now we learned how to drive with a single differential equation, a single ODE. Now we're going to learn how to do it with a system of ODEs. Now, I gave you 2 examples last time of where systems of ODEs arise. The first one was when we did order reduction. We had a second-order ODE. We converted it to 2 first-order ODEs. If you have a third-order ODE, you can do the same. You'll get 3 first-order ODEs and so on. Okay? But there are other cases where you immediately just get a system of first-order ODEs. Chemical kinetics is one of the primary examples that chemical engineers deal with for systems of ODEs. But there's also other cases, and the case I'm going to give today is modeling a pandemic like the COVID-19 or the flu or something else. And we'll build that together. However, I want to give you a little synopsis of how ODEs are typically built. This is one strategy to think about when you are analyzing a system and you're trying to build relations between rates of change, right? Because the argument, initially, my argument was it's easier to relate rates of change than to develop an answer or a formula for the quantity directly. So this is one strategy to build, to think about ODEs, and it's called compartment model for ordinary differential equations. So let's see how this works, and then we'll go and apply it to model a pandemic, and then we'll learn how to solve a system of ODEs using ODEint. Okay? So we're still learning how to drive. Now we're going to learn how to drive a truck, essentially, a system of ODEs. All right. So first, consider a department store. This is a gorgeous building over here for the department store. Now, the store has a number of people in it. Suppose, like initially, when you take a snapshot of that store, it could be, the South Town or whatever. There's shoppers, there's employees, there's solicitors, whatever. Bunch of people in there, right? Different, babies crawling all over the place. Okay. Now, designate by n the total population inside that department store. Okay? Nothing mysterious here. Now, the store also has an entrance and an exit. Okay, so people come in through the entrance, and people can leave through the exit. Okay? The rate of change of the population n inside that store, inside that compartment, okay, depends on how many people are entering and how many people are leaving. Just basic conservation, right? And here's how to think about it in terms of ODEs. If people are leaving the store, then we expect the population to decrease. That is, the time rate of change of n to be negative, right? So in other words, dn by dt is equal to minus r out, or the rate of people leaving the store. Okay? So let's say there's 10 persons leaving per hour, right, of that store. So then dn by dt is minus that rate of change, people going out. However, we can dig a little bit deeper into this because we don't know that rate. But you can try to guess what that rate is. And you could argue that the larger the population in the store, the more people are likely to step outside, right? As you put more people in, there's more likelihood that people are going to leave that store. So that R out on the right-hand side is actually proportional to the population itself. Just like the population of lobsters, if there's more lobsters, right, the rate of increase of that population is proportional to that initial population itself. The more lobsters there are, the more babies they're going to make. So that right-hand side is going to be a little bit larger. So you could argue that, well, in this case, the rate of change of the population is proportional to the population itself with a negative sign because people are leaving. So the rate of people leaving the store is proportional to the number of people inside the store, right? When everybody leaves the store, n becomes 0, and then dn by dt becomes 0, right? So that is consistent with what logic tells us. Similarly, if people are entering the store, then we expect the population to increase in the store. That is, the time rate of change of n will be positive. Now, there's one important thing here to consider, is the right-hand side, is that going to be a positive number or a negative number? If it's a positive number, it means things are increasing. If it's a negative number, it means things are decreasing, okay? So in this case, if people are coming in, we expect that the rate to be proportional to the number of people coming in. Now, you could argue that that rate, Rn, is proportional to the population outside the mall, right? So you could say this is equal to some coefficient beta times the population outside of that mall, okay? Now, you clearly are going to need an equation for I, which is the population outside the mall. So then you would need another compartment for the population outside the mall, and you can balance the two with each other. In general, for any compartment you consider, there are things coming in and things that are leaving. Basic conservation, okay? So that idea of conservation, you probably studied it with reactors now, mass flowing in and mass leaving. It's the same thing with ODEs. It's just a rate that is coming in and a rate of things leaving. So this is best illustrated with an actual example. So we're going to build a compartment model now for a pandemic like the COVID-19. We're going to take the simplest model possible. We're going to build it together. It really takes 2 minutes, right? We're going to consider 3 populations. The population of susceptibles, those are the people all of us walking on the planet, walking on the streets, you know, enjoying our life, right? And we are susceptible, however, to be infected by a virus, right? So that's the population that is susceptible to be infected by a virus. Then you have the population of infected. Okay, so those of us who get infected are going to move from susceptible to become infected. And then there's also the population of recovered. Okay, so those who have been infected and then they recovered, they're going to move from the infected compartment to the recovered compartment. Okay, it's literally these three compartments, all right? So initially, we're going to start with the susceptibles. The susceptibles, once exposed to a virus or a contamination, they're going to lose from that category, right? They're going to lose based on how much infection they're being affected with. So this looks like ds by dt equal minus R1. Okay, R1 is the rate at which the susceptible people are being infected. Okay, now we can do better. You can say that the rate of depletion depends on how many susceptible individuals there are, right? So then you could say that rate of depletion of susceptible people going to infected is actually proportional to the number of susceptible people, so that's minus alpha s. But that's still not 100% true, because a susceptible person will only get infected if they interact with an infected person, right? So how do you represent an interaction of S and I, or susceptible and infected? How do you represent that mathematically?
Well, susceptible is going to be initial S minus I. So
Susceptible, no. But if I had one infected individual and 999 susceptible, how do I represent the interaction? Or if I had two infected and 998 susceptible, how do I mathematically represent that interaction? Pardon me? Yes, so that would be the coefficient. The rate of infection is how infectious a virus is. However, if you had more infected people, right, you're more likely to infect the susceptible. So it's actually a product. The product of the number of infected people by the number of susceptible people gives you a good representation of the interaction between the two, right? So if you had one infected person and 1,000 susceptible, there's, you know, less likelihood that that infection is going to pick up very quickly. But if you had 100 infected people and 1,000 susceptible, then those 100 times 1,000 is going to increase the number of the interactions, right? So by taking the product of I and S, okay, and some coefficient beta, that gives us the rate of change of, so susceptible people are losing from their compartment at a rate of minus beta is. Beta is some coefficient, which is a property of the virus we will see later. But I times S is the critical thing to realize here, is that when an interaction happens between two things, okay, that is represented mathematically by a product. So in your homework, you're going to be doing a predator-prey model of foxes and rabbits. Okay, and we're going to represent an interaction when foxes and rabbits meet and there's predation going on. Okay, that representation is a product of foxes times rabbits. So when you see a product between two quantities, it means there's an interaction between the two. Okay, so now we have our first differential equation for the rate of change of the susceptible people. Okay, ds by dt is some coefficient negative beta is. So negative means we are losing from the susceptible people into the infected category. Okay, so now with the infected, we have, so from the susceptible, we only have one way out, right? There's nothing going back in because we assume once you're recovered, you have permanent immunity. Okay, so there's no way for recovered people to become susceptible. You can make that model if you want, but right now we're not going to do it. But for infected people, okay, there is people becoming infected, right? Okay, but there's also, so the number of people being infected is actually equal to beta s, right? Beta is, right? Because those are the people that left susceptible and became infected. So it's negative beta is up there, but it's positive beta is over here. That's the conservation. Whoever left from susceptible and became infected now entered the infected compartment. However, after a period of time, the infected people, okay, leave the infected compartment and become recovered. And if that rate is some recovery rate, like after 10 days or 14 days you recover from the infection, then you are leaving the infected compartment. So that adds at a rate gamma, that adds minus gamma I. There's no interaction there necessary, so I is not multiplied by anything else, right? So the rate of infected people being recovered, specified entirely by gamma, so that's negative gamma I, right? So you see the first compartment, everyone is leaving from the first compartment. When in the second compartment, the infected, there's people coming in and people leaving. They're coming in at the rate beta IS, and they're leaving at the rate gamma I. And finally, for the recovered, there's only one way in, right? So then d recovered by dt is equal exactly to the rate of the infected people being recovered. So you see how we build this in a conservative way, right? So everything is conserved. Whatever is leaving susceptible is entering infected. Whatever is leaving infected is entering recovered. So you see gamma I, beta IS, right? And now we have a model for pandemics, believe it or not. This is a basis model for a lot of epidemiological studies. They make this a little bit more complex. So one model, you could say, okay, what if after a year the recovered becomes susceptible again? So then you can draw an arrow from recovered to susceptible at a different rate, and then you can add that term there. What if you want to account for deceased and hospitalized? What if you want to account for social distancing? Nothing more complicated than this. You just add one more compartment, add a coefficient, and develop your system of differential equations. The challenge in real life is figuring out what those coefficients are. Okay, so beta, gamma, and in this case, we only have beta and gamma, right? Beta is related to how infectious the virus is. So when they say COVID is very infectious, it means beta is large, relatively large. Okay, for other diseases might not be as infectious. You would need a huge viral load to be infected, so then beta becomes smaller. So how do they measure these parameters? They do studies, and they take samples, they collect data, and they try to fit their results from the ODEs system into the actual data, and they get those numbers, and now they have a predictive model for what's going to happen in the future. So once you measure that for the flu, for the cold virus, for COVID, for example, then for next year, you know the infectivity of the virus is going to change a little bit. Maybe next year's strain is going to be a little bit more infectious because the virus evolved, then you change your beta a little bit, okay? So if you run this with some numbers, note here I modified the model a little bit. I divided beta by n to normalize things, but it's the same model. Those are the three equations, and you have three unknowns, S, I, and R. This is an example with some numbers looking at those three populations. In blue is the susceptible population. In red is the infected population, and in green is the recovered population. You see initially, in this case here, so on the y-axis, it's the number is 1,000. So initially, we had 1,000 people, total population, only one infected person and 999 susceptible. You see the blue line, most people were susceptible, and then there's one person who is infected, and then 2, and then 3, and then 6, and then 12, and then it exponentially picks up. Now, as people get infected, they're also recovering. So they're moving from the red to the green. So you see the green starting to pick up, and it's a little bit shifted to the right. And the red curve is consuming more of the susceptible. The green curve is consuming more of the red curve, right? And then until everyone is recovered with immunity, okay, at the end. Very nice, balanced curve, and kind of represents like, yeah, you know, this looks like what you would expect. 3 blue, 1 brown, if you've heard of that YouTube channel, he did a random animation of like, he put like one person among like 999 and then randomly moving and infecting each other, and he was able to randomly reproduce these curves. Okay, so there's a lot of veracity in these equations, okay? All right, now we're going to try to solve this together in Python. For this, we need to do a few things. First, we need to represent the system in vector form so that it looks like d by dt of something equal some right-hand side. Now, that something and that right-hand side, instead of it being a single scalar, phi, now it's a vector of unknowns, right? So S, I, and R are our unknowns, so we put them as a vector. And our right-hand sides can be also put in as a vector. And that's how we're going to solve the system. We write this as d phi vector by dt equal right-hand side. This is a vector also, 3 quantities of phi and t. Now notice, each equation could depend on all other equations. The first equation, which is the equation for S, depends on I. The equation on I depends both on S and on I, right? And the last equation on R, for R depends only on I. Okay, so there could be coupling across all different variables. Yes?
Is there a reason that the d/dt equation is negative?
Oh, no, that's a typo. Thanks, Andrew. Apologies about that. Let me fix it. That's a typo. Good catch. Thank you for that. Okay. There's no reason for that. That's a typo. Good catch. Okay. All right. So thankfully, ODEint also allows us to solve a system of equations, a system of initial value problems. The same way we used ODEint to solve a single equation, we can use it to solve a system of equations, except now this time we are going to provide it with the vector. Okay? So now if you think of that equation, the vector equation we have, that vector equation represents d phi z, the first ODE, the second ODE, the third ODE, and so on. And our full phi vector represents the first dependent variable, the second, and so on. Okay? So this is generic form. And the right-hand side vector represents the right-hand side sequence, the right-hand side for the first equation, right-hand side for the second equation, and so on. Okay? So ODEint allows us to do that. Still takes that same form. However, now, the right-hand side is simply a Python routine that returns a vector, the vector right-hand side of the governing system of ODEs. And must be at least of the form, again, right-hand side, phi and t. Okay? Now, in this case, phi is also a vector of the dependent variables, because your right-hand side depends on all of the dependent variables. So you must assume that your right-hand side routine also takes in a vector of all of those dependent variables. Your initial condition now becomes initial conditions. You have a vector of initial conditions, right, for all the dependent variables that you're solving for. And finally, time is a sequence of time points at which you want to solve for all of your unknowns, okay, all of your dependent variables. Okay, so for example, for the SIR pandemic model, your right-hand side is going to return right-hand side 0 for S, right-hand side 1 for I, and right-hand side 2 for R, recovered. Okay? And then your phi 0 is going to be the initial condition on susceptible, initial condition on infected, and the initial condition on recovered. And finally, T is just like a lin space, okay, like we did last time. Okay. When we were doing a single ODE, the return value of ODEint was simply a sequence of values for the dependent variable at the different times. So we're solving for phi. So the solution contained phi at t0, phi at t1, phi at t2, phi at t3. Now you're solving phi 0, phi 1, phi 2, phi 3, many phis at all of those different times. So the return value is going to be actually a complicated matrix. Not very complicated, but complicated matrix. And the first column contains the first dependent variables at all the times you want to solve at, from t0 all the way to t end. Right? So that's the sequence of points you're solving the ODE at. In the second column is the second the second ODE or the second dependent variable, and so on until the last ODE. Okay? Now, this poses a problem because you want to take that solution and then plot your solution. There are two ways to do this. In an OK way and an easier way. But the OK way is kind of more intuitive, perhaps, is to take each one of those columns, pick it up from solution, and store it in a variable, call it phi0. And then the same thing for phi1. Take all of that. You see how I'm using the semicolon here and taking the first column, the second column, taking everything in that column, okay? And then you can go ahead and plot phi0 and phi1, etc. Another way is to actually take the transpose of this matrix. When you transpose it, then you can grab each row and store it in a variable, okay? This will become clear once we get our hands dirty, okay? So, and one more thing, again, ODEint allows you to pass arguments to the right-hand side function. We're going to use that over here. All right, so grab your Jupyter notebooks. We are going to solve this system of ODEs for the pandemic and using these 3 ODEs. All right, let's do it. Sometimes discussing the syntax in abstract terms is a little bit overwhelming. It's like, I have no idea what you're talking about. And once you do an example, it makes so much sense. But I have to put that generic form in the slides so that when you're coming back to study this, you have the full description, okay? So this is the system we're solving. Let's create a new notebook. Okay? Pandemic model. All right? Zoom in a little bit. Oops, hold on. Looks like my Jupyter crashed. One moment. So we're going to just grab our boilerplate stuff, import numpy as mp, and then matplotlib inline, and then config inline back. I don't know why they don't do this just by default. Figure format equal svg, scalable vector graphics, import matplotlib.pyplot as plt, and then from scipy.integrate import ODEint, ODE integrate, okay? So I'm going to go ahead and copy the equations so that we know what we're solving, or I can just put them over here. I can just move the slides window. Of course, it doesn't move it entirely. Okay. All right, so that's what we are solving. All right. So what I would start doing is just hitting the right-hand side function. That's all we need, after all, for ODEint. In our case, our right-hand side is going to be a vector. Okay, it's going to return 3 right-hand side values in an array. And those 3 right-hand sides are going to be minus beta over nis, beta over nis minus gamma I, and then gamma I. Okay, And you're asked, where the heck are we going to get gamma, beta, I, and S, and R? Well, they're all part of that right-hand side argument. So let's see how it works. Define right-hand side pandemic. And again, this is going to take phi and t and a bunch of arguments. So I'm going to do gamma, beta, and gamma over here. Okay, beta and then gamma. Well, let me do it in Greek notation. Okay. All right. So now phi, you should assume, because you're solving a system of equations, you're going to assume that phi contains the vector of solutions of your susceptible, infected, and recovered, if you're solving them in that order. Okay? So in other words, your susceptibles are contained in phi 0, your infected are contained in phi 1, and your recovered are contained in phi 2. How do I know that? Because that's how this is defined. That's how the right-hand side for ODEint should be defined. ODEint, yes?
Sorry, what's that last Greek thing? I can't do the Greek thing, so I just type it out.
The gamma.
Gamma?
Gamma, yeah. So ODEint, if you're solving a vector of equations, because you're providing a vector right-hand side, is going to return you a vector of phi values in the order of how you provide the right-hand side. So we're going to provide our right-hand sides as the first right-hand side is going to be the right-hand side of the S equation. The second right-hand side is going to be the right-hand side of the I equation. And the third right-hand side is going to be the right-hand side of the R equation. So then automatically phi contains them in that order, S, I, and R. Once you have S, I, and R, and we're passing also beta and gamma, that's it. You can put right-hand side for S. Okay, what is the right-hand side for S is, let me move it here a little bit. Okay, let's see if I can squeeze this guy a little bit here. Okay. Okay, the right-hand side for S is equal minus beta over n. Okay, we didn't provide n. That's going to be another argument, the total population. Minus beta over n times I times S. Right-hand side I is beta over n times I times S minus gamma times I. And right-hand side of R is equal gamma times I. And now I'm going to return them in what order? In this order, the right-hand side for S, right-hand side for R, right-hand side for I, right-hand side for R. If I mess up the order, then the meaning of phis is going to change. Because phi 0 corresponds to the phi with the right-hand side of the first right-hand side. If you provide the right-hand side for S, that means phi 0 is going to be S. So make sure you conserve that order. You can order them however you like. Just make sure you are consistent. Okay? What I would do, just write the equations and reproduce those equations the same way you wrote them. So you don't have to think about it and get confused about it. Okay? So what I'm going to return is right-hand side S, right-hand side I, and right-hand side R. And that's it. That's all you need to do to solve this complex problem, to have those very nice, interesting curves. That's all you need. I mean, couldn't get easier than that. Systems of initial value problems. OK. So we're done with the right-hand side. Let's now actually solve it. We're going to start with a population of, let's say, 1,000. N is equal 1,000. Okay. This stupid doc always doesn't know where it needs to go. Okay. Initially, my initial condition for the infected is going to be one person. One person infected initially. Okay. So that means that, and also no recovered people. Nobody is recovered yet. Okay. And then finally, for the initial condition on S, the susceptible, so that's going to be n minus I0, right? The total population is 1,000. If one of them is infected, then there's 999 susceptible. Okay? So that's going to be n minus I0. Okay? Now let's set beta. Now I'm just making up this number so that the curves look nice. But the actual beta, they still haven't figured it out, I think, for the COVID. I tried to get some information from papers, and the numbers are all over the place. Okay? So we'll just put some 0.6. Now gamma, I know for sure that's actually 1 over the recovery, the number of 1 over the days to recovery, which is about two weeks for COVID. Okay? So 14 days. So we can put 1 over 14 days. Okay? Now, our end time, let's run this simulation for 100 days. Okay? Now, why do I know this is in days? Because that system, the units is actually, time is just done in days. Okay? So all of these rates are infected per day. Okay? So that ODE is done in days. Okay? Otherwise, the units, the coefficients will change. Right? So we'll do a, for time, simulate, or just time, is lin space now. Let me get it a little bit up here for those in the back to see. NumPy.lin space from 0 to t end. And we'll do, let's just do like 200 points. Okay? 200 points. So now our initial solution vector or initial condition is S0, I0, and R0. Remember the order in which we are solving these equations. SIR. That's why it's called the SIR model. Okay? SIR. And then finally, sol is equal ODEint, right-hand side, pandemic, and then initial condition, and then time. And then we need some arguments. Our arguments that we're going to pass are going to be beta, gamma, and n. So those args need to be in the same order as you put them in your right-hand side routine. Yes?
So gamma in this case, like people recover per day?
No. That's the recovery rate. How fast are you going to recover from the infection? It's 1 over the recovery rate. So it takes you 14 days to recover from the infection. Then that's 1 over 14. For yeah, I guess.
Well, if it's 100 days, it's 200 intervals, every interval.
No, this is, I'm just getting more points on that interval. So it's solving it every 12 hours, essentially. But that doesn't matter. So the number of points is strictly going to give you better accuracy. Okay, it's just going to give you smoother curves. Okay, but even if you do 100 days, this will just work. Okay. All right, so we solve this, and then, okay, it solved it. Then if you print sol, it's just going to be a mess, right? But at least it has 3 columns. And based on what I showed in the slide, the first column contains the value for the susceptibles, the second column, the values for the infected, and the third column, the values for the recovered. So how are we going to plot those? Simple. I'm going to use the better way. I'm going to say that S, I, and R are equal to sol.transpose. And finally, we can plot. plt.plot. We're going to plot time on the x-axis and S on the y-axis, blue, okay, and label is equal to susceptible. Then we're going to plot I in red and recovered in green. And we're going to say these are infected, recovered. I'm going to do a blt.grid. Okay, I'll give you a moment to catch up. If you executed this and got that plot, raise your hand. I need to see a smile on your face, like, yay. All right, now mess with the numbers, with the beta and the gamma, and see what happens. Okay? All right? Who else is getting that plot? Okay, good, good. Okay. Thought you guys would be excited about this. This is a model for the pandemic. Sure, sure. But it's a better example than just doing a reacting, you know, right? This is more relatable, right? Okay. Pardon me?
You said they were never very good at modeling this.
Well, yeah. But still, the ability, oh, look at that. Okay. Pardon me?
For some reason, I'm missing a curve.
You're missing a curve.
Oh, I see what I did.
Oh, yeah. You have to change the R. Yeah. Okay. So now change your beta, for example. Make it larger. You're going to get more people infected. You're going to get people infected much faster, right? Change the recovery rate. If people are recovering faster, right? If people are recovering faster, yeah, then, you know, we're going to be done with the pandemic sooner.
I'm getting an error at the Fsolve.
Can you scroll down? Okay, so let's go to RHS pandemic. You have phi t, you need to put n, the population. Yeah. Okay, so now if you change gamma, change beta, so gamma and beta are properties of the virus, right? So with this model, for example, or you're treating some, I don't know, infectious disease in a petri dish or something, you know, your model has a physical meaning. Those coefficients, they have a physical meaning tied into the disease in question, okay? All right. So maybe, you know, we make it more infectious, 0.9, and it takes forever to recover, like 30 days, 40 days, 30 days, right? So look at that. You immediately get everyone infected, right? Number of susceptibles just immediately done, but then takes you quite a while to get to this immunity, to this full recovery. Okay? Now here's a thought for you, which you're welcome to build upon or not, and present to me if you want. Take this model now and do something with it. So, for example, what happens if you add a social distancing compartment? Okay? So if our objective is to keep this red curve at, you know, let's say 300 people at any given time. No more than 300 people in our population are infected. Okay? Then if you have a compartment of social distancing, you could say, okay, as we approach 300 people, let's have more and more people social distance. Then as the curve starts dipping down, as the red curve starts dipping down, let's have people come out again. And then as we hit 300, let's have people socially distance and so on. And see what happens, you know, as you ride this curve to flatten it out and go to 0, okay? Could you do that? So add a compartment called distanced, and that distance is going to go between susceptible and distance, right? So some of the susceptibles are going to go on lockdown, And once the infection rates go low, then they're going to come back to susceptible. Okay? Think about that. Could you develop a system and solve it with ODE-int? What if you want to track hospitalizations and deceased? Okay? Add a couple of compartments. What if you have loss of immunity? Add from recovered going back to susceptible. Okay? If you think of something, you know, type it up and send it to me. Okay? I cannot confirm nor deny this. But I've had a few people propose for the last 2 years. So one had a very interesting model, deceased and hospitalized, because his argument was those are easier to track. If you're trying to build a realistic model, you can go and take measurements, you know, at a hospital, et cetera. You can add a vaccination. Let's say, you know, after 6 months, there's a vaccine discovered. Then there's a switch that just flattens out this curve, just goes down, right? So do all sorts of things with this, okay? If you have an idea, if you have a thought you want to build on, shoot me an email, say, hey, what do you think of this? And go ahead and build it, and, you know, we'll go from there, okay? All right. Systems of ODEs. Compartment models. They're pretty cool. You're going to see them once you hit kinetics. It's all about this idea, compartment models. Those compartments are reactants. Oh, reactant A combines with B, or reactant A goes to B and C, right? And you're going to have reaction rates, right? And then A reacts with B, then you have A times B, right? It's the same thing as I times S, right? So this is almost it's identical to kinetics. It's just easier to understand as people moving out of a compartment and going in than reactants leaving a compartment and reacting, okay? All right, let's take 2 minutes, and then we're going to start digging under the hood of ODE-int to see how the magic happens, all right? So under the hood of ODE-int, we're going to start with, the world of solving a differential equation numerically, and ODE numerically, is very busy and very dense. There's a lot of methods, and we will barely scratch the surface here. But scratching the surface accounts for a significant amount of intellectual effort that goes into these methods that solve ordinary differential equations. We're going to start with what we call explicit time integration. And the meaning of the word explicit is going to become obvious once we study implicit time integration, okay? So our objective, again, is to solve an ODE of the form d phi by dt equals some right-hand side r of t and phi. Okay? That right-hand side, again, could depend on phi, could depend on time, both of them, or none of them. Okay? With an initial condition of phi 0 at t equals 0, and on the interval t0 to t end. And all you know about that problem is this initial condition, phi 0, and you know the rate of change of phi, okay, from t0 to t end. Okay. That's the end. So our purpose is to find this curve. We don't know what this curve is, but suppose that it looks like this. Our purpose is to rebuild this curve numerically. So just like we did last time, and what I showed you last time, we're going to divide this interval into discrete points. This is called discretization. When we did it on the heat transfer problem, we did that discretization in space. So our domain was the rod. Along the length of the rod, we chose discrete points, and our spacing was delta x. Same here. We're discretizing in time. Our interval is delta t or h interchangeably. And you assign to each one of those points a time value. T1 is t0 plus delta t if delta t is constant. T2 is t1 plus delta t, and so on. Okay? No mystery here. And then our objective is to find these blue dots, which hopefully correspond to the points on that rat curve. And we're going to call those phi at t1, we're going to call it phi1. And phi at t2, we're going to call it phi2, all the way to phi n minus 1, and phi n plus 1, which are a representative discretization for the ODE. So at point n. When we did the heat transfer problem, we were using I. If you remember, we use phi I plus 1 minus 2 phi I plus phi I minus 1 over delta x squared, because it is customary to use I, j, and k for space and use n for time, okay? So once we do boundary value problems, we're going to switch this nomenclature from n to I and j and k, okay? All right, so we're going to collapse this right now. What we know is phi 0. What we don't know are phi 1, phi 2, all the way to the end, right? And then we're going to use this initial condition to recursively construct the unknown function values. Starting with phi 0, we're going to use information at phi 0 to build phi 1. Then we're going to use information at phi 1 to build phi 2, and so on, all the way to the end, okay, recursively. Now, here's an important statement. And you should agree with this. I hope you do. The governing ODE is valid at all of those points. Agreed? There's no reason for it not to be valid. This is a physical time domain. That ODE represents a physical process. So that ODE is valid. If we take that ODE and apply it at T1 and apply it at Tn or Tend, it is going to be valid. That ODE, we want to satisfy that ODE. It is valid there. We can apply it there. So that means that we can evaluate the ODE at any one of those discrete points. Now, since we only know the initial condition at T0, we start by evaluating the governing equation at that initial point. So we're going to say d phi by dt at T0. Now, pay very close attention here. Okay, this is kind of obvious, d phi by dt at T0. But the right-hand side is also evaluated at 0. It's very important to recognize that what's in the parentheses here is T0 and phi 0. Okay? Okay, great. d phi by dt at T0 equal r at T0 and phi 0. Next step is to use this equation to obtain some relation between phi 0 and phi 1. So what we're going to do, we're going to use a forward difference approximation. Remember the forward difference formula? d phi by dx was phi I plus 1 minus phi I over delta x. There's no reason not to be able to apply it here between 0 and 1. Okay? So that means that d phi by dt at T0 with the forward difference formula is phi 1 minus phi 0 over h, or delta t, that spacing between phi 0 and phi 1, plus some error, right? So now we're going to take that approximation and plug it, put it up there. So we get phi 1 minus phi 0 over h equal r at T0 and phi 0. Now we know T0, we know phi 0, we know r, we know how to evaluate this, we know phi 0, we know h. We can solve for phi 1. That's it. That's all that this method is doing. Once you have phi 1, you can use the same strategy to solve for phi 2. So then phi 1 is phi 0 plus delta t times r at T0, phi 0. So now go ahead and build phi 2, phi 3, and all the way to phi n plus 1 recursively. Just do a couple, and then you'll see the general formula. And put the time here. So T2 is T1 plus h. So that means phi 2 is phi 1 plus whatever. Okay? So the final exam is going to ask you to solve ODEs this way. I'm going to ask you to take 2 time steps, for example, okay, and solve an ODE to estimate the value after 2 time steps, for example. Okay, so what is phi 1? Anyone has phi 1? Ethan? No. Oh, sorry, phi 2. Phi 2, that's right.
P naught plus HR T naught B naught all squared.
Okay, so no, in terms of phi 1. So we're building this one step at a time, right?
Yeah, but it'd be P1 plus HR of T1 P1.
Correct, yeah. So phi 2 at time t2 equal t1 plus h, or t1 plus delta t, is equal to phi 1, the previous value, right? We're building this recursively. Phi 1 plus h times r at t1 and phi 1. Okay? Now, it's important to keep it this way. If you were to bring phi 1 and substitute it over here, it gets very complicated. It becomes r of r of r of r of r, right? It's not worth it. Okay, that's not how you do it. You just build it one step at a time. Okay, build it recursively. Same thing if you continue. Phi 3 is phi 2 plus hr at t2 and phi 2, and so on and so forth. So we're using information from the past to predict the future. Okay? Now that's a terrible idea. It's like driving and looking in the rear view mirror, right? That's the problem with this method. But anyway, it gets us, it does a lot of work. Most problems can be solved with this very simple method. Okay? In general, we described this method called the forward Euler method. Forward Euler's name is everywhere. It's like, what is the forward Euler method? In the context of time integration, this is the forward Euler method. It says that the value of the function in the future at n plus 1 is equal to the value just one instant in the past plus that time instant times the right-hand side evaluated in the past. Now, that's why we call this an explicit method, because all you need to know is the values in the past, and you can predict the future one step at a time. There's no implicitness involved in any of this. Okay? That's called the forward Euler method. A pseudocode for this, or an algorithm for this, is that given some state at t0 or tn, and phi n and tn, your delta t, your right-hand side, then you can build that solution one step at a time. You start from 0, you go to 1, you go to 2, to 3, all the way to your desired end time. This is essentially what ODEint is doing on the back end. There's some more complicated solution methodologies going over there, higher order Runge-Kutta and adaptive time stepping and all sorts of stuff. But the idea is the same. For simple problems, this is the method of choice. Believe it or not, we use this method for very complex computation fluid dynamics calculations because it's simple, it's clean, and when it works very well. Okay? Now, if you remember, this from Hidden Figures, again, going back to Hidden Figures.
We can calculate long-term landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Hey, we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be only math. Something that looks at the problem numerically and not theoretically. Math is always dependent.
It is.
Euler's method.
Euler's method.
Yes.
But that's ancient.
It's not ancient. Science is not ancient. It's like 300 years ago. See those derivatives? And so anyway, so what she ends up solving is the trajectory for the trajectory for the orbit trajectory to predict where we need to launch and where the orbit is going to be like. Okay, so she predicted this over time. Now, what they're showing on the board is nonsense, but that's actually what she did. I just want to show some fancy numbers on the board, right? All right. So Euler's method, very important. OK, so let's do an example together. And on purpose here, I chose a slightly daunting example. On the right-hand side, you have phi to the power 4. OK, so that you might think that this is a nonlinear problem. It is nonlinear for the ODE, but once you put the forward Euler method, it doesn't matter if you have monkeys on the right-hand side, right? Because it's always using information that you know. It's using information from the past, OK? So what I want you to do now is take this ODE, OK? d phi by dt equal minus t squared phi to the power 4 with an initial condition of phi 0 equal 1 with the formula phi n plus 1 equal phi n plus h times right-hand side tn phi n, okay, with a time step of 0.5 seconds. So h is 0.5 seconds. The first thing you want to do is express the right-hand side in this generic formula in terms of the actual ODE. So instead of r of tn phi n, substitute the actual right-hand side. So put in what the right-hand side is in this formula so that we can actually solve it next. So keep it in terms of phi n plus 1 equal phi n plus h times, what is the right-hand side in this case? There's so many Euler's methods. It's actually unclear what they're referring to in the film, because there are other Euler's methods in orbital mechanics as well. So you're not wrong. But you know, for the purposes of this class, this makes the point. So she did actually have to predict the orbit. Yeah. All right. So anyone has got the formula? Yeah. Pardon me? On my line? Oh, T3. Thank you. I'll just delete this. Quick fix. I just erased it. Oh, it's still doing that. I actually had T4. So, yeah. Just erase it. Okay, there you go. I erased it too. So. All right, so Todd?
Is it phi n plus 1 equals phi n plus h times negative tn squared times phi n?
To the force, that's correct. Yep. So the first thing you would do is substitute your right-hand side into the formula. So on the exam, I give you an ODE, or on the homework, or in real life, you get an ODE, you have the right-hand side, you want to use the forward Euler method. Just first thing you do, just plug in that right-hand side into the formula. So that you know now, if you're indexing in n, you're starting from 0, then phi 1 is phi 0 plus 0.5 times negative t0 squared times phi 0 to the power 4, and so on. Okay? So now, let's actually calculate this using your calculator, or just kind of doing it by hand. Okay? So starting with phi 0 equal 1, now let's get phi 1 at t1 equals 0.5 seconds, okay, using that formula.
So nowadays, for that thing they did in the hidden figures, would they just put those numbers in a computer and they just spit out the answer?
Yeah, but the computer is doing something, and someone has to program that computer. If we run out of people like you who can program this, right? Yeah. Have you watched it? Have you watched it? Yeah, it's a fun film.
Will it eventually get to a point where all the math can be put in the computer, so there's no more math that needs to be done by humans?
Well, still, but we are creating the theory, right? We're creating all of this to put on a computer, right?
What if we made it so computers could make this?
Well, that would be essentially the direction we're headed in with artificial intelligence, right? But artificial intelligence is going to be based on collecting data, right? So, all right, so phi 1 is phi 0 minus h times t0 squared times phi 0 to the power 4, and h is 0.5, t0 is 0, so that still is 1, Okay, so now let's do phi 2. Okay, go ahead and do phi 2. Yeah, so phi 1 is 0. So you can take, if you didn't do phi 1, that's fine. Sorry, phi 1 is 1. Just take phi 1 as 1, and then proceed to do phi 2. Just apply that formula. Yes, yes. Yeah. Because that's the right-hand side, right? So that's minus t squared phi to the power 4. Okay? So for phi 2, n is equal to 1, right? If you can just write it down, if you don't have to punch it in the calculator, that's okay. Just get phi 2. I want you to be able to get those, punch in those numbers correctly. Okay? Okay. So phi 2 is phi 1 times h right-hand side at t1 and phi 1, which is phi 1 minus h t1 squared, phi 1 to the power 4. You just simply substitute the numbers. Phi 1 is 1, h is 0.5, t1 is 0.5, so they get 0.5 squared, and phi 1 is 1, so 1 to the 4, so you get 0.875. Okay? Now do phi 3. Trust me, you're gonna be doing this on your final exam. Yeah, definitely. All right, phi 3, and we'll stop at phi 3, okay? In your mind, phi 3 is only going to depend on phi 2 and t2. That's the Euler method. Phi n plus 1 only depends on information at n, okay? Only on previous information. Phi 3 only depends on phi 2. Phi 4 only depends on phi 3 and t3. Information at the previous time level. Yeah, so, yeah. Right, no, that's probably the numbers are fine. But just write, so you don't make a mistake, write out the symbolic, yeah. Yeah. Because if you get a complex right-hand side with like sine phi and cosine, and you're just going to get really complicated. Okay, so I would always write it down symbolically and just replace the numbers. Phi 3 is phi 2 plus delta t times the right-hand side at t2 and phi 2. Everything at 2, right? So phi 2 minus h t2 squared phi 2 to the power 4. You just simply substitute the numbers. Now notice phi 2, we brought it from up there, 0.875. Delta t or h is 0.5. And then t2 is 1, so that's 1 squared, and then phi 2 is 0.875 to the power 4. Then you get that number, and you build your solution one step at a time. Did I make a mistake?
No, I just have a question. So in the movie example, they were trying to calculate trajectory.
Yeah. So yeah, they would have an initial condition like with speed and position in the atmosphere, for example, right? And then they want to study the trajectory around the Earth, right? So you're putting him in orbit, yeah. Yeah. Okay. So we have 2 minutes. We can push this until next time. But if we were now to program this, now we know how to do ODE_int, okay? And in practice, you're going to use ODE_int. I just need 1 minute of your time. If we were to implement this in our own Python subroutine, which we're going to do next Tuesday, because we need to do an example where this is going to fail, okay? ODE_int almost never fails. But if we were to do this, like what if you had to create a routine for the forward Euler, what are the arguments for that routine, and what would you want to return for that routine? So you need delta t, h, right? An initial condition, and the or if you're giving it delta t, right? You need t end. You can either give it an array of times or delta t and t end, right? Either one of those. And the initial condition, what else? What else? The most important piece of the ODE. The equation or the right-hand side. because you can always assume you're solving d phi by dt. The left-hand side is always d by dt. But it's the right-hand side that changes everything. All right? Okay, you guys have a nice weekend. I'll see you on Tuesday.